Okay, welcome back everyone. In this segment, we're going to be talking about derivatives and how they can help us calculate instantaneous velocity and acceleration. So these are the same essential questions that we had before. We're looking at position, velocity, and acceleration using derivatives, and then also how do we solve problems involving straight line motion with constant acceleration. So here's just one quick review question from our previous two slideshows. And so from this position time graph, we want to draw the corresponding velocity graph. And to do this, we remember that velocity is the slope of position versus time. And if we just call this 1, 2, 3, and -1, -2, -3, we have a slope of 0, a slope of -5, a slope of 0, and again, here we have a slope +3 and a slope of 0. And that goes for 1 second, and 1 second, and 1 second. Okay, so what does our velocity time graph look like? Well, we have a slope of 0 for the first second, and then it's kind of going to jump, but we'll have a slope of, let's just call this -5. And that would be for the next second. And it's going to jump around again to 3, wherever 3 is, which is probably right here. If that's 5, this will be +3-ish. Oh, sorry. First we went back to 0. And then we jumped up to 3. And then we jumped back down to 0. And you'll notice that I'm kind of being nice math-wise, whereas I'm including certain points, and then when the function is not continuous, we're taking care of that. Okay, now in real life, you wouldn't have these sharp corners. You would have curves like this, because you can't instantly change from one velocity to another. And so what would happen is that these graphs would kind of go like this in real life. So this is just something very important to keep in mind. So we could have very large slopes, but we won't have infinite slopes. Okay, so what if we need the instantaneous velocity, but we don't have a graph? So we have functions as x depends on time. Well, that's where we bring in the calculus. We could graph it and take tangent lines, but doing derivatives is a lot better. Okay, so instantaneous velocity sort of comes from our definition of average velocity, but remember that what we did is we said, well, let's take the slope as points A and B got closer together on that graph. Whoops. And so if I had my graph here and I had points A and B, as A and B got closer together, I would get basically the slope of the tangent line. And that is the instantaneous velocity. It's the limit as t goes to 0 of v average. So technically as delta t goes to 0 of delta x over delta t, which we write as dx dt. So I know that many of you are coming to this class with different degrees of calculus knowledge, so I'm going to try to explain some of the calculus concepts as we go along. And this is the most important one for right now, that instantaneous velocity is the limit of average velocity as delta t goes to 0. So this is the derivative of position with respect to time. That's how we write this. Okay, now instantaneous acceleration is the same concept, but we replace position with velocity. So again, it's as delta t goes to 0, the limit of the change in velocity over the change in time. And so this is acceleration, the derivative of velocity with respect to time. Now, one application that we're going to see later on is the second derivative, which is where we take a derivative or a change in x with respect to time. So that's a first derivative, otherwise known as dx dt. And when we take the limit of that, as that change goes to 0, we get the second derivative with respect to time, which is written as d squared x dt squared. Another way to think about this is that we are taking d dt, the derivative with respect to time, of dx dt. And this is why you see this as d squared x dt squared. It's a weird way to write it, and there's many different ways to write derivatives. Another way is if it's with respect to time. So x is our function, x is a function of time. The velocity is sometimes written as simply x dot, and that means dx dt. So that means that acceleration, which is dv dt, or d squared x dt squared, is sometimes just written as x double dot, second derivative of x with respect to time. So we won't worry too much about that. Okay, so I kind of wrote over this, but think of the d as a baby delta, indicating a very tiny change. All right, so how do you do derivatives? Well, it turns out that there are some very easy rules, and this first one is called the polynomial, or the power rule. So if we have a function x is equal to a t to the nth power, then the derivative of that is n a t to the n minus 1. And we're not going to prove this in this course, but you could do so using properties of derivatives and limits. And we're just going to use it. So first of all, we have a particle that travels from a to b using this function, that x is equal to 3 minus 6t plus 3t squared. We want to calculate velocity and acceleration as functions of time. Okay? So first of all, v of t is going to be dx dt, and the derivative of a constant 3 is 0, because basically we have t to the 0, so that would be, remember that if we have x is equal to a t to the n, then v is going to be n a t to the n minus 1. So if n starts out as 0, 3 is basically the same thing as 3 times t to the 0, because t to the 0 is 1, then we have 0 for that term. Negative 6t will turn into negative 6, because t to the 1 will turn into t to the 0, and then we'll have plus 6t. So basically what you do is you multiply the coefficient by the exponent, and then you reduce the exponent by 1. Acceleration as a function of time will be dv dt, and this will just be 6. Okay. And we can also find the instantaneous velocity at 6 seconds. So v of 6 is going to be negative 6 plus 6 times 6, which is 30 meters per second. And the initial velocity, v naught, that's going to be basically the value of v when t is 0. So we take our function for v of t, which is negative 6 plus 6t, and we plug in 0 for that, and we get negative 6 plus 0, or negative 6. That means that our initial velocity was negative 6. Here's another example. Now we have a function that's to the third power. So v of t is the first derivative, dx dt. So that's going to be negative 4 plus 6t minus 3t squared, and the acceleration will be the derivative of that velocity. So it'll be 6 minus 6t. So what's the instantaneous acceleration at 6 seconds? That would be a of 6. So that would be 6 minus 6 times 6, which is negative 30, and we would assume meters per second squared. Okay, so we're going to take a moment and get into the kinematic equations. But actually now is a good place to stop, so we're going to do the kinematic equations next time.